Hello everyone, this is my attempt to kind of discuss cellular respiration for YouTube. I'm gonna go over my my two methods that I use to memorize, and which ones I think will really help, should help other people. Number one is the draw method. I like to draw things out, so whenever you want to memorize it, don't just look at the actual graph. You should draw it out. So I like to draw the entire cellular respiration out. So basically what I'm going to do in this video. Another method, back to draw method. Another thing you can do for that is when you just say the next day, I wouldn't look at any notes or anything, and right off the bat, maybe after you're done with your morning routine, just try and attempt to draw the entire cellular respiration. Whatever you don't get, so don't look at any notes. Whatever you don't get, that's what you know to actually memorize and to actually keep on studying, and what you actually do know. So that's also a really good way of testing what you know, what you do know, and also drawing it puts a visual in your head using your hand and everything else. The next method is a word bank method. This method I just came up with. We don't use the actual words, but we plug in the accounting values, you could say. For example, in glycolysis, which I'll go over for each one, you have to make a chart of what you use, a word bank, I say, of what you use and what you produce. For example, in glycolysis, you use 2 ATP, you use 4 ADP, and you use 2 NAD+. So this would be my word bank for my using of glycolysis, and I'll show you how I use that method. And then for producing, I know that I produce 4 ATP, but remember that 2 ATP is being used by glycolysis. And then I know I also produce 2 NADH. And all I would do is take these and try to plug them in to wherever I need it to be, and that's how I would use that method. And I'll describe that more when I start talking about the cellular respiration. So we can go ahead and start talking about cellular respiration now that I've done talking about the memorizing strategies. So the first step in cellular respiration is glycolysis. So we'll do glycolysis. Now it all starts with a glucose molecule outside of the cellular membrane. And remember that glucose is a pretty big molecule, so it will use facilitated diffusion. I don't know how to spell, sorry. Facilitated diffusion, and you have your glucose molecule, which is C6H12 and O6. I'm gonna write this as glucose because this is basically glucose. All right, so your glucose molecule will come inside the cytoplasm. So now we're in the cytoplasm where glycolysis happens. Glycolysis happens in the cytoplasm. And you still have your glucose. I'm gonna remove facilitated diffusion, and I'm just gonna write FD for that. Just so you guys could keep that there. Now, again, for my word bank method, I said we used 2 ATP, 4 ADP, and 2 NAD+. So now I can kind of remember, oh, okay, well, this is our energy investment phase. I'm going to write energy. This is our energy investment phase. So an energy investment meaning we're going to be using energy. So ATP is our energy. So I know ATP will go here, our 2 ATP. Our glucose molecule is going to be broken down into different things. And when we use 2 ATP in the molecule, we're going to be coming out with 2 ADP. So this just means that if we're using the ATP, it will turn into ADP. So that's where we get produced, and we had our 2 ADPs produced. Now, again, this is just something where you kind of have to memorize the word. I'm going to remove facilitated diffusion out of here. This is something where you're going to have to memorize the words, but the word would be dioxy. For the one side only, it would be dioxy. Sorry, my fault. Dihydroxy acetone phosphate. And now we kind of have to remember that glucose, remember, has 6 carbons. Glucose has 6 carbons. And now dihydroxyacetone is broken down and it is 3 carbons. Same with this next one, which I'm gonna drop down to here. So the next one is called, you can call it G3P, but the full name is glyceraldehyde 3 phosphate. Or you can call it G3P. And this also has 3 carbons. Now we want to bring down this one, and this also equals G3P. So just think about dihydroxyacetone phosphate as an extra step for one side, but we're also going to have G3P on this side. Another G3P, which is also another 3 carbon. Now, for the final step of glycolysis, it's going to go down into pyruvate, which is again a 3 carbon on both sides. And now, again, we have our word bank. So we already used up our 2 ATP, but we have 4 ADP and that we used, and we use also 2 NAD+. So if you just remember the word bank, you know it goes somewhere on this graph. And if I remember correctly, we will be able to put in 2 ADP here on this side and 1 NAD+ on this side. That will be what we use. And what will be released is, again, I did not fully produce it, but we produced 4 ATP and 2 NADH. Again, what will be released here with 2 ATP and 1 NADH. So remember, the NAD+ is the empty truck, and NADH is a full truck, so it's getting an electron. So NAD+ is getting an electron, and it's going to be put into NADH. And the same exact thing is on this side. All right, so this should be our glycolysis, our full glycolysis. Now, remember, I like to remember this as remember when Dr. Sada was talking about the long list and the small list? You basically have two identical, you have this one, sorry, let me use a different color. You have this reaction, and you have this reaction, which is completely exactly the same. It's the exact same reaction. So the only difference here is to know that we have an energy investment phase of using 2 ATP, and we have an extra phase called dihydroxyacetone phosphate. And then all you have to remember is kind of just one chart. So I like to remember this side of the chart going down this way. And I like to remember that whatever from this side down would be the exact same on the other side. But you do have two sides that you go down. And this would be for glycolysis. Now, from glycolysis, if you do not have oxygen, If you do not have oxygen, so if you right here, no ox. If you have no oxygen, what you are left with from the glycolysis is your NADH, your pyruvate, your other pyruvate, another NADH. So the whole thing without no oxygen is, again, fermentation. So this process is called fermentation. And the whole thing is the NADH needs to be turned into an NAD plus, or else we won't have enough empty trucks to keep storing. And we also need to get rid of pyruvate, because if pyruvate is not gone, then it will back up the system and it will break down. So what we do is we ferment. So the NADH to NADH will reduce. The word reduce means gives an electron to pyruvate. So we'll reduce both pyruvates, and we'll get another 2 NAD plus back, which the 2 NAD plus will go back into this system right here. Those arrows are confusing, so I'm going to remove them. But the NAD plus will go back into glycolysis to, again, make another 2 ATP. But the whole thing is the electrons will break down pyruvate. And for an animal cell, I'm going to write cell for all of them, and a yeast cell. And for bacteria, will be, again, variable. That we'll learn in microbiology. Yeast will be ethanol. An animal would be lactic acid when you reduce pyruvate. And that's fermentation. That's all you need to know for fermentation. Fermentation is taking pyruvate, adding an electron to them, which is reducing them. And for an animal cell, it would be lactic acid as your product. For yeast cell, it would be ethanol, which is your product. And for bacteria, it would be variable. And that is it for fermentation. So now, we will go over pyruvate oxidation. Pyruvate oxidation takes place in the matrix of the mitochondria, this is, I'm going to write down all the words for it. That is your outer membrane. Oops. This is going to be your inner membrane. This space in between is going to be considered your inner membrane space. So inner membrane space. And that will come in handy later when I describe more about the later steps. But all we need to know is when we have oxygen. So I'm going to draw a line here. This is going to be when I'm just going to write have oxygen. Have O2, which is O2 is oxygen. When we have O2, this is going to happen. So we have our product of pyruvate still. We have a product of NADH. And we have another product of NADH. That. And another product of pyruvate. Actually, another product of pyruvate. So, I'll write it over here so it's not confusing. We have 2 pyruvate. And we have 2 NADH. Now, when these enter the cell, the double matrix, into the matrix of the mitochondria, so this space right here, in this space would be the matrix, right down over here, mitochondrial matrix. While they're entering the cell, the pyruvate will lose 2 carbons, which will release in carbon dioxide, so CO2. It will release to CO2, and it will also create, it will actually use NAD plus 2 of them to create another 2 NADH. Now, our 2 pyruvate will create, I'm going to write it up here, will create 2 acetyl-CoA. I don't think he told us in class, but CoA also stands for coenzyme A. Maybe he did, maybe he didn't, but it also means coenzyme A. So now we can look at this, and we already know that somehow these 2 NADHs from glycolysis will also enter the matrix. So I'm going to write another 2 NADH because these 2 NADHs came from here. So if I highlight it, it would look something like this. I'm going to highlight this 2 NADHs are these 2 NADHs. So that's where that came from. Those 2 NADHs are also in the matrix, but we also, through this process is called pyruvate oxidation. couldn't fit everything on there, but pyruvate oxidation. Pyruvate oxidation will create two CO2. It will also create two NADHs, and it will also turn it into two acetyl coenzyme A's. And then we also received another two NADH from glycolysis. So this whole process here is called pyruvate oxidation. I think it's the easiest part because all you're doing is turning two pyruvate into two acetyl-CoAs, and you're producing two NADHs, and you're also producing two CO2s. So that is it for pyruvate oxidation. Now we'll move over to the next section, which is going to be we'll move over to the next one, which is going to be Krebs cycle or citric acid cycle. So Krebs, we either call it Krebs cycle or the citric acid cycle. Now, we start off with two acetyl-CoAs. Now, this is the hard part, and I'll also help you guys memorize this. Our word bank for the Krebs cycle is a total of, pretty sure we have a total of 6 NADHs. We have a total of 2 FADH2. We have a total of 2 ATP. And that should be it. That is our word bank for citric acid cycle. And I'll tell you exactly where all of them go. So we'll start off by adding. We're going to add. Our first step is add oxaloacetate. We add oxaloacetate. And remember, I almost forgot to mention this. The acetyl-CoAs lost 2 carbons. And pyruvate has 3 carbons. So we have 2 pyruvate, which means we have 6 carbons here. 6 carbons. And we lost 2. That means we have 4 carbons. But each acetyl-CoAs are going to be 2 carbons. But since we have 2 acetyl-CoAs, that means we have actually 4 carbons. But each acetyl-CoA are 2 carbons each. The oxaloacetate, though, has 4 carbons. And we're adding them together. And since we're adding them together, we're going to get 6 carbons, and we're going to turn that into citrate. Citrate, which has 6 carbons. Then an extra step added is going to be isocitrate, which also has 6 carbons, and nothing is going on in this step, which is 6 carbons. Now we're going to start losing carbons. Our next step is going to be, I'm gonna change this over here and make it smaller. All right. Our next step is going to be alpha. I don't know how to do the sign properly, but alpha keto glutarate. All right. Now this one has 5 carbons. And since we lost a carbon, again, when we lose carbons, we lose it as CO2. But remember that since we also lost CO2, we're on this step. Remember, our word bank says we gained 6 NADHs. For this one, we also gain NADH. And remember that this is only one cycle with one acetyl-CoAs. This cycle actually happens 2 times because we have 2 acetyl-CoAs. I should actually keep that up there. Now, from ketoglutarate, I'm going to make this smaller. I'm going to make it a little bit smaller. From ketoglutarate, we're going to go to the only one that I will tell you now that don't have an ATE at the end. All of these have ATE at the end, and we'll go through them. Most of these have ATE. The only one that does not have ATE is succinyl. I don't know how to actually say it, but succinyl coenzyme A, CoA. This one has 4 carbons, which means we lost another carbon dioxide. And again, we used another NAD+. I did not write it here. Plus. We use another NAD+ over here. And we produce another NADH here. Now, from succinyl coenzyme A, we will go over to succinate. Succinate. Another AT at the end here. This one, I remember the 2 S's in between will remove an ATP through SLP. I'll write the whole thing out. It's going to be substrate level phosphorylation. So substrate level phosphorylation is going to be can make this ATP. Again, that's only one cycle, so it actually makes 2 ATP. And it also makes these two net ATPs on glycolysis. Substrate level phosphorylation, Dr. Saad went over in class, makes 2 ATP, then 2 net ATPs from glycolysis, and the 2 ATPs in the Krebs cycle. So that's where your 2 ATPs come from. Now, the next step after succinate would be fumarate. Now I'm running out of space here, unfortunately. I think I can reduce this. Actually, I can reduce this whole thing here. I'm gonna make this smaller here. Fumarate. Now the byproduct of fumarate, let me actually make this a bit smaller. And also kind of like twist it a bit. All right. The byproduct of fumarate is going to be FADH2. And that will use an FAD. So we use an empty truck. The empty truck is FAD. And remember, I remember this as fumarate that starts with an F. Right before it, we're going to make another F, or FADH2. So that's how I remember when to know when you make your FADHs. And that is the only time you will ever use FAD and make FADH2. The only time in the cycle, the entire cycle, is that you'll be dealing with FAD and FADH2. So it's another thing to know when to use NADH or NAD and FAD over FADH2. Now, for the last step in the cycle would be malate. Let me actually write it down first. Right here. Malate. Again, another one with ATE. And remember, fumarate has ATE. So every single one of them has ATP except for succinyl coenzyme A. And that's how we remember ATP comes after the one without 8. So if it does not have an 8, which is succinyl coenzyme A, does not have an ATE like the rest, like oxaloacetate that has an ATE, citrate has an ATE, isocitrate has an ATE, ketoglutarate has an ATE, and the only one that doesn't have an ATE is succinyl coenzyme A. That's how you know right afterward it's going to make ATP. Now, from fumarate to malate, nothing happens, but from malate back to oxaloacetate, we make another NADH. That means we used NAD+. And since oxaloacetate is 4-carbon and succinyl is 4-carbon, that means, that's how you know, once you reach succinyl coenzyme A, which is a 4-carbon, we cannot really lose any other carbons because when we get to oxaloacetate, it is a 4-carbon molecule. So succinate will be 4 carbons. Fumarate will be 4 carbons. And malate also will be 4 carbons. So again, to recap, glycolysis will make byproducts of pyruvate and 2 NADHs. So we have 2 NADHs from glycolysis entering the cell. While pyruvate is entering the cell, it's being oxidized, oxidation, and it's making 2 acetyl-CoAs, which are 2 carbons, which means it's also releasing 2 CO2s, and it's also making 2 NADHs. So at this stage right here, we have, at pyruvate oxidation, at this stage right here, we have 2 acetyl-CoAs. We actually have 2 CO2s, 4 NADHs, and 2 acetyl-CoAs. But that we don't really have to worry about, but we'll write it down. Acetyl-CoA. So now, as you can see here, we have 4 NADHs from this reaction. Now let's go over how much we have. So remember that this cycle happens twice, not once, but twice. So everything you yield will be by 2 times. So let's go over it. From oxaloacetate all the way to citrate, all the way to isocitrate, nothing happens. But as soon as we go from isocitrate to ketoglutarate, we make CO2 and NADH. So we make times 2 of that. Same thing from ketoglutarate to succinyl coenzyme A. We have CO2, we have NADH, and we multiply that by 2 because we're doing 2 cycles. From succinyl CoA, I don't know how to say it, to succinate, we have ATP. And remember, we're also multiplying the ATP by 2. Again, from succinate to fumarate, we're producing FADH2 and we're going to multiply that by 2 because we're going in 2 cycles. And then from malate to oxaloacetate, we have another NADH, which we're going to be multiplying by 2. So in total, we have 2 4 carbons we produced 4 CO2 from the Krebs cycle. We produced 2, 4, 6 NADHs. As you can see, we have one right here, we have one right here, and we have one right here. But you're going to multiply them by 2. We have 2 FADH2, and we also have 2 ATPs. So, now in total, if we add them right here, we have 2 CO2, which will again be released through simple diffusion out of the membrane. So we actually don't have to worry about carbon. So don't worry about carbon. That will be released outside the membrane as waste, what you breathe out. That's waste. What we really want to look at is the actual things that will make us our energy, or ATP. We have 4 NADH over here as well, which we can add onto this. So we're going to add 4 NADH, which will give us 10 NADHs. Okay. A good thing to remember, I'm going to write it in this space and remove the double times. Good thing to remember is, actually I should write it over here. Good thing to remember is NADH, 1 NADH yields 3 ATP. And 1 FADH, 2 equals 2 ATP. Sorry if it's conflicting with you guys. This means if we have 10 NADHs, we have 30 ATP plus our 2 FADH2s, which will be 4 ATP. So if we actually draw this out, I'm going to add 4 NADHs over here and make this a 10 NADH. So that will be equal to 30 ATP. This will be equal to 4 ATP. We have 2 ATP from this cycle right here. We produced 2 ATP on this side, but remember we also produced 2 net ATP on this side. So the 1 ATP was used, the 2 ATP was used, but we also produced a 2 net ATP. So that means we have another 2 ATPs. And those 2 ATPs will be another 4 ATPs. A lot of numbers. And this will equal 38 ATPs. I'm going to have another video on the oxidative phosphorylation where I have it drawn out, and I'll be right back. All right, guys, this is back with completing the cellular respiration. I have pretty much everything set up, so it shouldn't be too long. This is just from the previous slide that we were going over. The last thing we talked about after the Krebs cycle was our net gain of NADHs, ATP, and FADH2. So I put that all on. I put that all in one slide here. We have 6 NADHs from the Krebs cycle, which again we have to remember. We get 2 from going to ketoglutarate. We get 2 from going to succinyl coenzyme A, and we get 2 from going from malate to oxaloacetate. Then We have 2 NADHs from glycolysis. We have 2 NADHs from pyruvate oxidation. We have 2 FADH2s from Krebs cycle. We have 2 ATP from glycolysis through SLP. I forgot to write that down. Through SLP. Through SLP, which is again substrate level phosphorylation. And here as well. The rest of the ATPs will be made with the process oxidative phosphorylation. And we'll talk about that more later. So yeah, that is our net gain. And we also talked about how each NADH equals 3 ATP, and how each FADH 2 equals 2 ATP. So now we have a total of 6 here plus 2, which is 8, plus another 2, which is 10. So we have 10 NADHs. We have a total of, again, 2 FADH2, that doesn't change. And we have a total of 2 ATPs from both, so that will give us 4 ATPs. So if we add this up, 10 times 3, because we have a net gain here of 3 ATPs, and we want to convert 10 NADHs to ATPs. So this will give us 30 ATPs. FADH, we have 2 of them, and we have 2, so multiply 2 by 2, we have 4 ATPs. And then we have another 4 here, which stays the same, which gives us our total of 38 gained ATPs. And that's the whole process of oxidative phosphorylation that I'm about to go over, but this is just the numbers. So now we can remove this layer. This is what we're going to be basically using for we're going to be using this as our model. Okay. So we'll start on this side. All right, so remember that we have 10 NADH. We'll start off with NADH because NADH and FADH2 both have different pathways. So the whole process is going from, well, we have to first talk about the parts inside the inner membrane of the mitochondria. So let's talk about what the mitochondria. This is, again, I talked about, this is our outer membrane. This right here is our inner membrane space, and I'll write it over here. And then this is our actual inner membrane right here, which I'll actually draw on this side here. I just don't want it to take up the space. Inner. So now that we've talked about the actual parts of the, well, we also have the matrix here. This part, anything inside this part is going to be the matrix. But we have that there. Now we talk about the parts that is used for the electron transport chain and chemiosmosis. So chemiosmosis, all you have to remember, chemiosmosis is the last part. We'll talk about the last part because it's the last one. So this is going to be ATP synthase. Actually, no. I don't want to confuse you guys. We'll start over from complex 1. We'll start off from the beginning. This is going to be called complex 1, this guy here. Complex 1. I'll use numbers. This guy is going to be called, can you guess it? Complex 2. And then you have a complex 3. And you wouldn't guess it, but you have a complex 4. And I'll go over all of these in a second. So those are our complexes. They do not move at all. These 4 complexes do not move at all. We have 2 transporters in between them. We have one transporter that transports items from complex 1 to complex 3, and it also transports items from complex 2 to complex 3, and we'll show that. This guy here, this transporter, its name is called ubiquinone. No, or none. In the book it says none. Or ubiquinone, you can put ubiquinone. That transporter will transfer items from complex 1 and 2 to complex 3. We have another transporter whose name is called cytochrome C. And this guy transports items from complex 3 to complex 4. So now we can start talking about the electron transport chain. So the electron transport chain is the movement of electron through these complexes. So let me write. Through the electrons through the complexes. So NADH is a full truck of electrons. The NADHs have electrons. And what it's going to want to do is from inside, I should actually put this inside right here, inside the matrix, because after the Krebs cycle, it's actually inside the matrix. NADH will go to complex 1. Okay? Now, complex 1, from complex 1, the ubiquinone, will go ahead and collect the items. A bit smaller. The ubiquinone will go ahead and collect the items from complex 1. The electrons. It will collect the electrons from complex 1. It will not go to complex 2. Remember, from NADH, it goes to complex 1. Then the ubiquinone will go. The electrons actually don't go in this particular space. The ubiquinone will actually travel over to the complex 1, pick up the items, and then it'll go to complex 3. So the ubiquinone will go ahead and drop it off at complex 3. From complex 3, let me draw it like this because I'm going to have to draw more arrows. From complex 3, it'll go to cytochrome C. So cytochrome C will go ahead, pick it up from complex 3, and cytochrome C will take it to complex 4. Now that we know the movement of electrons of NADH, this is only for NADH, we can see here that it does not go through complex 2. It only goes from complex 1, the ubiquinone will take it to complex 3. Complex 3, the cytochrome C will take it to complex 4. Now, as this is doing it, the NADH is shooting out hydrogen ions. Okay? Complex 1, it shoots out hydrogen ions. Once it gets to complex 3, it shoots out hydrogen ions. Once it gets to complex 4, you guessed it, it shoots out hydrogen ions. And we'll talk about what they do later. So that is all that NADH does. NADH will go to complex 1. And remember, when NADH drops off the electrons, this will turn into 10 NAD plus empty trucks, which again will be cycled back into glycolysis, pyruvate oxidation, and again Krebs cycle. So we will have empty trucks. That's something to know. The NADH will dump electrons, will become empty trucks again. The electrons will go from complex 1, it'll shoot out hydrogen ions, and ubiquinone will go pick it up, take it to complex 3. Complex 3 will shoot out hydrogen ions. Complex 3 will take the electrons to cytochrome C. Cytochrome C will take it to complex 4. Complex 4 will shoot out hydrogen ions. Now we have to talk about FADH. And I'm going to write that. I'm going to make this smaller. And I'm actually going to erase this, just so we have more space. Actually, I'm not going to erase it. I'm just going to make it smaller. Okay. So now we have our F, and actually, I should have done that on a different page, shouldn't I? Yeah, it's fine. F, A, D, H. And I'll actually do this on a different one. Okay. F, A, D, H, 2. We have, remember, 2 FADH2 that has electrons as well, but it has a different path. FADH2, instead of going to complex 1, we'll go to complex 2. From complex 2, the ubiquinone, again, will go to complex 2 and pick up those electrons. From ubiquinone, it will take it over to complex 3. From complex 3, the cytochrome C will pick it up, and cytochrome C will take it to complex 4. So as you can see, it pretty much has the same cycle except for complexes 1 and 2. NADH goes to complex 1, FADH goes to complex 2, and NADH does not go to complex 2. So again, we can see just with the the NADH path, and we can see it with the FADH path. Now, as for hydrogen ions pumping, electrochemical pumps, complex 2 does not pump hydrogen ions. However, the hydrogen ions from F8DH2 will be pumped from complex 3 and in complex 4. But just in smaller quantities. So again, the only electrochemical pumps are complex 1, 3, and 4. Those are the only 3 that pump out hydrogen ions, not complex 2. Okay? Now we have all these hydrogen ions. We emptied all our trucks. Now what do we do with the hydrogen ions? And also, what do we do with the final electrons that are produced, that are kept in complex 4? So let's talk about that first. My bad. Trying to get this out of the way. All right. We can use, hello. The electrons have to go somewhere. The electrons have to be accepted to a final acceptor. So the thing we call this is the final electron acceptor. And that's going to be water. It's going to be turned into water. It's going to use hydrogen, H2. 1/2, this is the equation, 1/2, or plus, should actually, plus 1/2 O2 equals, and I'm going to write down here, actually I should do H2O, because 1/2 of O2 is oxygen, 1 oxygen, and you have 2 hydrogens, which is equal to water. So this is where your electrons are going. Your electrons are going to be taken up and made into water. So water is your final electron acceptor. So all the electrons from NADH and FADH2 will go through the cycle, the electron transfer chain, and go and make water. That is the final electron acceptor. And that whole process is called electron transfer chain. That whole process we talked about is electron transfer chain, all the way until the final electron acceptor. Now we have all these hydrogens. We have hydrogen here. We have a hydrogen here. We have hydrogen here. And we also have hydrogen all the way over here. So I'm going to bring them all together over here in one big group. One big group. All the hydrogen come over here into this one spot right here. Now, why over here? This is what we call ATP synthase. The actual, this blue and orange molecule here, or whatever I drew, is going to be called ATP synthase. And so that is what it's called. The chemical reaction, or what is going on, the reaction that's going on is going to be called chemiosmosis. I don't know how to spell it. I don't know if it's with the, I think it's chemiosmosis. I might have spelled it wrong. Might have an E, CHEMI, M-E-E. chemiosmosis. But the whole thing, the ATP synthase needs to be powered, and we use the power of hydrogen ions, which have created an electrochemical gradient. So an electrochemical gradient meaning this side inside the matrix has a negative, and inside the inner membrane space is positive. It creates a battery. The hydrogen ions create a battery inside the inner membrane space. Now we got to use that battery to power the ATP synthase. The hydrogen ions will be forced down here, down through ATP synthase to turn it on. And ATP synthase will take a phosphate and an ADP and combine them. So the equation for that would be, I don't know what color to use. We'll use this color. The color. So the equation would be I know it's too dark. ADP plus a phosphate, which is P, equals ATP. So this chemiosmosis is using the hydrogen ions that was shot out by the complex 1, 3, and 4, not 2, 1, 3, and 4. It was sent to ATP synthase. It was shot back into the matrix, the hydrogen ions, called chemiosmosis. And now, since the ATP synthase is powered, all it's doing is this reaction. This molecule is carrying out this reaction all the time. And that is how our ATP is made. So this whole process, the process called, I'm going to remember if I can. The process of electron transport chain plus chemiosmosis, I think it's E, don't take my word for it. Chemiosmosis equals, I'm going to make this smaller. Keep doing this. Equals oxidative phosphorylation. That is both of them combined. That is this whole process right here, oxidative phosphorylation, the combination of electron transport chain and chemiosmosis is the oxidative phosphorylation. So let's do a quick review again. Starting here with glycolysis. Glycolysis is breaking down of glucose, which is C6, H12, and O6, that is glucose, is taken. Inside the cytoplasm, 2 ATPs are used to break down glucose into 2 different types of molecules. You have a dihydroxyacetone phosphate which is a 3-carbon. And then you also have glyceraldehyde 3-phosphate, which is also a 3-carbon. Eventually, dihydroxyacetone phosphate will also become glyceraldehyde 3-phosphate, which is also known as G3P. G3P will then become pyruvate. And during that process, it makes 2 ATP and it fills 2 trucks with electrons, making NADH. If we do not have oxygen, so no oxygen, the pyruvate will ferment or be reduced using NADH's electrons. The NADH will give electrons to pyruvate, reducing it. For animal cells, it will become lactic acid. For yeast cells, it'll become ethanol. For bacteria, it's just a variable. It could be different depending, and you'll learn that in a different class. If we do have oxygen, our 2 NADHs will come over into the matrix of the mitochondria. And then the 2 pyruvate, while entering the matrix through the outer and inner membrane, it will be converted. It will lose 2 carbons. Both pyruvates will lose 1 carbon each and be turned into acetyl coenzyme A with 2 carbons. It will produce 2 CO2 or carbon dioxide, and it will also produce 2 NADHs. At this point in time, we have 4 NADHs, 2 carbon dioxides, and 2 acetyl-CoAs. Our 2 acetyl-CoAs will combine with oxaloacetate, which is a 4-carbon molecule. And then it will produce a 6-carbon because a 2-carbon plus a 4-carbon will equal a 6-carbon. And we will get a 6-carbon citrate. From citrate, we'll go to isotrate, which is another 6-carbon, doesn't do anything. From isocitrate, we'll go to alpha-ketoglutarate, which is a 5-carbon, which means it lost a carbon dioxide, and it gained an NADH. From alpha-ketoglutarate to succinyl CoA, we lose another carbon, so we have a 4-carbon molecule now. It lost a carbon dioxide and gained an NADH. After that, it's sent to succinate, which gained an ATP, and it's still a 4-carbon molecule. From succinate, it goes to fumarate, which is another 4-carbon molecule, but it gains an FADH2. From fumarate, it goes to malate, which is another 4-carbon molecule. Nothing happens between that. From malate all the way to oxaloacetate, it gains an NADH. And again, both of these, this cycle happens twice because we have 2 acetyl coenzyme A's. After the Krebs cycle, we have our electron transport chain. For NADH, it will go to complex 1. It will shoot out hydrogen ions. It will not go to complex 2. The ubiquinol will pick up the electrons and send it to complex 3. Complex 3 will shoot out hydrogen ions. And then the cytochrome C will pick up stuff from complex 3. And then it will send it to complex 4, which complex 4 will also shoot out hydrogen ions. Then we have FADH. The electrons from FADH will go to complex 2. From complex 2, the ubiquinol will pick it up and take it to complex 3. Complex 3 will shoot out hydrogen ions from FADH2. And then cytochrome C will pick up the electrons from complex 3 and send it to complex 4, which will also shoot out hydrogen ions. So for FADH2, the only 2 complexes shooting hydrogen ions are 3 and 4. And for NADH, the only 3 complexes shooting out hydrogen ions are complex 1, 3, and 4. The electrons at complex 4 are then sent to the final electron acceptor, which is water. And that is it for electron transport chain. For chemiosmosis, the hydrogen ions sent into the inner membrane space, creating an electrochemical gradient, is sent to the ATP synthase, which needs to be woken up using a battery or being charged. It sends the hydrogen ions back into the matrix, powering the ATP synthase on. And all the ATP synthase does is to take an ADP and a phosphate and make it into adenosine triphosphate, or ATP. And that process is called chemiosmosis. Those two processes together, the electron transport chain and chemiosmosis, equals oxidative phosphorylation. That would be it for this lecture. If you guys have any questions, just let me know. Thank you. Have a good day.